Hello, ladies and gentlemen. Oh, goodness. Again, I have the freeze on. I'm so sorry. Let's start talking about our objectives of the day. We are on our 5th unit of Chapter 8, and we're actually going to be jumping into Chapter 8 now. So our Unit 8 is going to consist of a chunk of information from Chapter 7, Sections 5, 6, 7, and 8 that we just did our quiz on Friday. And then all of Chapter 8. Okay, so we're starting ahead in Chapter 8. Because this is the first section of Chapter 8, it's just kind of introducing a lot of the topics we'll talk about later, so it's not super difficult. Okay, we're going to be talking about the greatest common factor, which is something that we have been talking about in math for a while now. It shouldn't be brand new for everyone. This should be kind of a review. So we're going to start by talking about what is a factor, and to be able to find something's prime factorization. Okay, how can I figure out what its prime factorization is? And when I show you that, it should look pretty familiar. We're next going to look for the greatest common factor. We abbreviate it by calling it a GCF. And we're going to look at that and how to do that with numbers. And then we're going to do a little fun, real world example. So let's go ahead and get started. What are factors? Okay, factors are whole numbers multiplied to find a product. Okay, for example, let me give you two factors. Two factors of the number 30 would be 5 and 6, because 5 times 6 makes 30. Okay, they are multiplied in order to find some other bigger product. Those numbers 5 and 6 in this case aren't the only factors of 30, but they are two factors of 30. Some other factors of 30 might be 3, because 3 divides into 30. Okay, you're looking for numbers that will divide in evenly. Generally, they're matched up because you have to multiply 3 by something to get 30. So 3 is a factor of 30, and so is 10. The prime factorization of a number is just its prime factors. I basically boil down, for example, the number 12 into a list of numbers that are prime. Okay, a list of numbers. You can see I'm multiplying. A list of numbers that are only prime numbers that make the number 12. And we generally leave off the number 1 because that one's just kind of obvious. So 1 and 12 multiply to make 12. But the thing is, 12 isn't prime. 2 and 6 make 12, but 6 isn't prime. 4 and 3 make 12, but 4 is not prime. And these here, again, we don't usually put the 1 because it's not really any extra information than we already know. But again, 4 is not prime. So this here is the prime factorization of 12. In this case, we have 3 numbers that we have listed. It could be 4, it could be 5, it could be 6, it could be just 2. Okay, the number 5, its prime factors would just be 5 because it's a prime number. Usually we find the prime factorization by doing something called a factor tree. And again, this is not super complicated. It should be a nice, easy, suave step into Chapter 8. But the factor tree works like this. Okay, look at the number 15. Figure out 2 things that multiply to make 15. I'm sorry, 30. Gosh, I'm so sorry. Look at the number 30. Look at the number 30. Find 2 things that multiply to make 30. 2 and 15. You could do, let me show you here, you could do 5 and 6. Doesn't really matter which ones you start with because everything that is not prime continues to be broken up. So I would have to break up 6. In this case here, I would have to break up 15 because it's not a prime number. Okay, prime numbers have no factors that go into themselves besides 2 and 1. 2 is a prime number because the only thing that divides into 2 is 2 and 1. Okay, so that's just the definition of prime. The number 6 is not prime because I can split it up between 2 and 3. 5 is prime because the only 2 things that I can multiply to make 5 are 5 times 1. Okay, so 2 is good the way it is over here in my example. I'm going to get rid of this just so it's not super, wow, that's slow, messy. But 2 is good. 2 is prime here, so I'm done with him. But I do need to split up the 15. 15 splits up into 3 and 5. Those are all prime numbers, so the prime factorization of 30 is 2 times 3 times 5. And yes, we generally put them in order from littlest to biggest. Let me show you how you could have done this doing it a different way. If you do that 5 and 6, which I had, 5 is going to stay the same, 6 goes into 2 and 3, and you will notice that I have exactly the same three numbers. 30 is 2 times 3 times 5. Okay, so prime factorization, usually we use a factor tree. Okay, if you have any questions, you can go back and listen to parts of that, but I'm going to move on. As an example, let's find the prime factorization of 24. Why don't you guys do it? Pause me, come back, and see if you have the right answer. All right, I think that you're back. I don't know how you guys started splitting this up, but I'm just going to do, 4 and 6. And this becomes 2 and 2, and this one becomes 2 and 3. So my prime factorization is, 24 splits into 2 times 2 times 2 times 3. But we usually don't leave our answer like that. Okay, we make it look a little bit neater, a little bit nicer. I don't have to write all three of these 2s. I can write 2 to the third power times 3. All right, so that should be our answer. I might want to check it. This would give me 4. 4 times 2 would be 8. 8 times 3 would be 24. So, yep, I'm good. That is the prime factorization of 24. 2 to the third power times 3. Anytime you have things written more than once, you can use an exponent to just kind of simplify it in a way that looks a little more simple, looks a little easier. If you have a prime factorization of 2 times 4 times 4 times 5, these could be 2 to the second, 4 to the second times 5. Okay? That's just a convention that we do. Next slide here is finding the greatest common factor. Okay, finding the greatest common factor. We have 2 different methods of finding the greatest common factor. Generally, I use this one, method 1, and that's just to list. I'm going to list all the factors of 2 specific numbers, and then I'm going to find the biggest one. Just to review, what is the greatest common factor? The greatest common factor, it's just like it sounds. It is some number that 2 things have in common as a factor, but it's the biggest of them. Okay, let me do an example. This comes into play. Do we use this in fractions? A little bit, but not so much. We use the least common multiple when we do fractions, but I want to find the GCF, the greatest common factor, of 2 and 18. Now, you might be 12 and 18, sorry. You might be looking at 12 and 18 and saying, oh, well, 2 goes into them. 12 divided by 2 is 6, and 18 divided by 2 is 9, and let's see, 3 goes into 12, and 3 goes into 18. These are all great. These are common factors. But we're looking for the biggest one. What is the greatest one? What is the largest one? So I generally list. I list 1 and 12 are factors of 12. I list 2 and 6. I list 3 and 4. Okay, it's easy to list them as little matches that multiply together. 18 is 1 and 18, 2 and 9, 3 and 6. What is the largest one you guys see? It is 6. Okay, it's the greatest common factor. The biggest common factor, the greatest common factor is 6. The second method that we have is to use prime factorization. Okay, so the prime factorization of 12 and 18. If I were to find them, I would do, 6 times 2, which is 2 times 3 times 2. Okay, if I were to do 18, I would have 9 times 2, and this would be 3 and 3. So I already have this written here. I wanted to show you where it would come from. But the prime factorization of 12 is 2 times 2 times 3. The prime factorization of 18 is 2 times 3 times 3. What I'm looking for are the common factors, and I multiply them. Okay, so they have a 2 in common, and they have a 3 in common. So I take 2 times 3, 2 for that one there, 3 for this one there that they have in common, and 2 times 3 is 6. Okay, so that's what's basically going on with greatest common factor. If you have any questions or comments or things you want to clear up, make sure and write them down, or go back and watch the video, and just take note of anything you want to ask tomorrow. What we're going to do tomorrow with greatest common factor in class is, because this is algebra, we're going to start looking at what is the greatest common factor between 4xy and 2x. Okay, we're going to start adding variables in here. Okay, what are some things they have in common? And this would actually be, 2x, because 2x can divide into both of them. Okay, so we're talking about how this works with variables. So let's just get the basics down with numbers, and we'll expand it to polynomials with variables tomorrow. Last but not least, we're going to do a story problem. James is creating a web page that offers electronic greeting cards. He has 24 Valentines and 42 birthday designs. He wants to display everything in a really nice little chart here where here's a row, here's a row, here's a row. And he doesn't want any sort of rows with missing space. Is basically, he wants the Valentines and the birthday cards to not appear in the same row. So he's not doing Valentine's birthday, Valentine's maybe a birthday and a birthday. He wants all of one type together in the same row. Okay, so we have Valentine's, 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 and then some groups of Valentines, and then, which one is, yep, then some birthday. Okay, and he wants to make some sort of rectangular diagram that looks kind of like this. How is he going to split up his rows? He could do many different options. Okay, something that they might both have in common as a factor, a common factor for both 24 and 42, I guess, would be 2. He could just do birthday, 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 and then go down, go down, go down, and then have Valentine's, Valentine's. But then he'd have a really, really skinny table. And it would go, 24 plus 42 is 66. It would be 2 wide and 33 long. Seems a little bit like it's not the most efficient use of space. Okay, so let's look for some common factors that might be larger. How do you guys think this is going to work? Why don't you try it? Why don't you come up with a guess of how many cards per row and how many total rows he'll need on his page. Okay, you may want to draw a picture, you may want to draw a diagram, but this is a question of looking for the greatest common factor. That might be a hint. So give it a try and come back. All right, when I look at, I hope that you're back and you're done and you have a guess. When I look at 24 and 42, I'm going to, first of all, be kind of light bulb moment that, hey, GCF is going to be 6. That is the greatest common factor that goes into 24 and 42. So does that seem to work? Does that seem to work? Could I have rows of 6 cards? Could I have, what do we have, Valentine's again? And then some of those, and then birthday, 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 birthday. Okay, and have some of those, and then have my last rows be completely full. Okay, I don't want any sort of like blank spots here. I want everything to be full. Well, let's see. I have, how much of each? I have 24 Valentine, and I have 42 birthday. So my Valentines are going to be 4 total rows, because 4 times 6 makes 24. And then with my birthday, I would have 7 rows, because 7 times 6 makes 42. So my cards per row, I'm going to do 6. And how many total rows? Well, I would have 4 of the Valentines and 7 of the birthday, so therefore I'd have 11 rows. Okay? And that kind of makes sense because when you add 24 plus 42, you get 66. And these two numbers will multiply to make 66, so that should be correct. Hopefully you guys had that. Hopefully you're feeling good about your notes. These were our objectives. Make sure we know what a factor is. We know what prime factorization is. Remember, make sure we know what greatest common factor is. And then make sure that we're clear about how that last problem worked. If it seemed fuzzy, if it seemed like you weren't really sure, go back and review it again. But otherwise, I will see you guys in class tomorrow. Have a great weekend.